All right. We're going to get started here. Geothermal heat pumps 101. It's a little bit loud. I'll wait for that door to get closed. So this is a session very introductory. We're talking 2,000-foot view. What is a heat pump? How does it work? What are ground loops? I'm assuming people in this room, with maybe the exception of a couple, don't know what a geothermal heat pump is or a ground source heat pump. So this session is going to go over all that information for you. So for me, my name is Amanda Schneck. I work for WaterFurnace International. We are a US-based water source and geothermal heat pump manufacturer. We're based in Fort Wayne, Indiana. My job with the company is I am the Northeast sales manager. So New York State has been my territory for the last 14 years. I've been a NY-GEO board member for the last, I believe, 2 years, and a founding member of the organization 10 years ago. So, looking at this crowd, I remember the first geothermal conference we had was 10 people. The second New York Geothermal Organization meeting, we had about 30. So there's more people in this room right now than we had at our second meeting. So it's truly impressive how the industry has grown over the last 10 years. So thank you for joining me. I'm gonna start a little bit with the history of geothermal or ground source heat pumps. So a lot of attention now with incentives, but really the technology was first patented in 1912 out of Switzerland. There was a patent published, and there really wasn't much work done until the 1930s, where people started using what's called an open loop system. That's when you're using groundwater directly through the heat pump to extract and reject heat into the water. So in the 40s and 50s, utility company was looking at different ways to not use groundwater, and they explored suitable piping materials. In the 1970s, there was plastic pipe innovations that now have given us the closed loop systems that are the most common in both residential and commercial applications. So I feel like geothermal gets a lot of attention within the last 10 years, but it's really been around for over 100 years. So let's talk about what is geothermal. Now there's two types, and they often get confused. The first type is a high temperature geothermal. That's where the core of the earth, you're going down hundreds and hundreds, thousands of feet, and you're extracting high temperature from the earth. That is typically used for electricity generation. Our technology is not that. We are low temperature geothermal. We're going down maybe 5 feet, maybe 500 feet, and now with the passage in New York of the 500-foot rule, we can go beyond 500 feet. But really what we're doing is we're harnessing the stored solar radiation in the upper layers of the Earth's crust. So the picture on the right, I know the font is small, but a little over 50% of the sunlight, solar energy, is absorbed by the Earth. And that is what we're using a heat pump to extract and reject heat into that more shallow depth of the earth. So here's a map of the US. You can see the Northeast, we're average between 52 and 42 degree ambient ground temperature. So if you go down 30 feet, 60 feet is what this map is showing, you're gonna have a constant, stable, average 50 degree ground. So if you think of a heat pump, what is a heat pump trying to do? A heat pump is trying to maintain a thermostat set point in a room. So if you have a ground that's at 50, you just need to get to 70 degrees. So we're just making a lift. Heat pumps make a lift of 20 degrees. Where if you think about an air source heat pump, the outdoor temperature is not constant. It's hot in the summer when you're trying to reject heat to the air. It's cold in the winter, so you're getting kind of an opposite effect. So this map really showcases that solar energy in the earth that we're harnessing to basically get the efficiency for our systems, that existing energy that's stored. So there's basically two ways to start. We look at the two laws of thermodynamics. You cannot get more energy out than you put in. That's the first law, the conservation of energy. And the second law is heat energy flows from areas of high heat to an area of low heat. So that's where you're getting heat transfer. So we'll talk about that more as we get into the basic geothermal system. So a geothermal system typically has 4 components, but what you would look at is you start with the geothermal piece. That's your earth loop component. Many different shapes and forms, we'll go over that. It can be horizontal, it can be vertical, it can be groundwater, it could be wastewater, and it could be a closed loop in a pond. Water and antifreeze are circulated through a pipe in a closed loop system, and that goes to a heat pump. The water that goes to the heat pump does not distribute through the building. I think there's a kind of a misconception there. The water that goes to the heat pump goes back to the ground. It's just a way to exchange heat back and forth. So within the heat pump, there is a heat exchanger, a water to refrigerant heat exchanger. So refrigerants you've probably heard of R22. The industry currently uses R410A, and we're in the process of switching to new refrigerants. But it's that refrigerant that's absorbing that energy from the ground and then going through a refrigeration cycle to get that lift, that extra 20 degrees to make 70-degree air. So there's 3 main components. Geothermal systems use electricity, just like an air source heat pump. There's no combustion, no fossil fuel. They're electrically powered systems. So the parts of the system that use electricity, you have your compressor, you have a fan motor, which can be called a blower, and a circulation pump. And that pump is what circulates your groundwater in your closed loop fluid, or if you have an open loop system, you would have a well pump. So there would be a pump outside in a well, just like you would have for domestic if you had a drinking water well. So let's talk a little bit about efficiency, because that's really one of the main benefits of geothermal. So the way the equipment is rated, so it's the physical heat pump equipment that carries the rating. Cooling, we use the energy efficiency ratio, or EER. That's the BTU output divided by power watt input. So a BTU, if you do not know, is a British thermal unit. It's the amount of energy required to raise 1 pound of water 1 degree Fahrenheit. So heat pump equipment has a BTU output rating, and it's based off of that, how much energy, 1 pound of water, 1 degree Fahrenheit. And then for heating, we use what's called a COP, or coefficient of performance. So that's BTU output divided by input. This, if you multiply by 100, would be a percentage. So we're going to look at an AHRI certificate, and I'll kind of show you how this works. So in other terms, we're putting in 1 unit of electricity to run the pump, run the compressor, use the fan motor, and then we're moving the energy from the ground, that 50-degree ground. That's the free energy from the sun, from the earth, that we're utilizing in the building. We're not having to combust anything to harness that energy. So residential equipment, I just want to note, you can see here there's an EER and a COP. There's 2 different types of heat pumps. There's units that make hot and cold air, and units that make hot and cold water. So a water to air unit uses, the water is your geothermal side, and then air is your, ductwork or fan coil or something like that. These are the efficiency ratings. So this is Energy Star Tier 3 ratings, and this is what is required to get tax credits, and it's a minimum efficiency. So a COP for a ground loop, which is a closed loop, is 360% efficient, is the minimum efficiency. So that's worst case of the year, 32-degree entering loop temperature. You have 360% efficiency. It's impressive. Average systems run 4 to 6% efficiency throughout the year because they're going to have higher water temperatures coming to the equipment. This is a worst case situation. Groundwater heat pumps, because you're using actual groundwater, not a closed loop, they have higher efficiency standards. So you'll see the heating COP as a minimum is listed as 4.1, or they need to be 410% efficient. Water-to-water equipment, which you're using your geothermal water, your heat pump is making hot and cold water, those have a little bit lower efficiency standards. So for a closed loop, you have 3.1 or 310% efficient, and then with an open loop system, you're looking at 3.5. Energy Star only applies to residential equipment, but in states like New York or states where there's incentives, they often use this as a benchmark to say whatever equipment you put in has to be this minimum or higher. So I wanted to put that in because though it's residential, it has been applied to commercial at times. This is an example of a AHRI certificate. So they're the third party that rates the equipment. There's a little hard to see, but there's 3 different loop types on here. There's a water loop heat pump. That's a boiler cooling tower setup, not a geothermal system. Then you have the groundwater heat pump. That's your open loop. And then there's a rating category for a GLHP, or a ground loop heat pump. That's your closed loop geothermal system. So oftentimes if people are taking advantage of incentives, this certificate is required based off of your heat pump model number to prove that the unit meets the efficiency standards. This is the third-party proof. So let's dig in a little bit more to the 4 different components of a system. So we've got a distribution circuit, we've got our heat pump or our refrigeration circuit, we've got our earth loop circuit, and we have our hot water circuit. So examples of distribution circuits, we have ductwork. So that's your forced air system. Heat pumps are reversible. They're making forced air hot and cold air. And then you have, for water-to-water applications, you can have low-temperature radiators, so you can send hot water to those machines, or a radiant floor is another example. So the heat pump itself, the refrigeration circuit, this is kind of an example of a unit without the front panels on. The bottom section, you can see a control box, and behind that is your compressor. And then above it, you have your blower, and to the right of that, you have your coil. So what happens here is the geothermal lines get connected, I wish I had a laser pointer, but to 2 lines, a supply and return from the field, because your earth loop is it's a closed system. It's staying in the ground. What you take out, you're putting back in. That heat energy goes through this graphic here. This is a cutaway of a coaxial heat exchanger. And if you're interested, I have one up here you can look at. But basically, water flows through the middle, and then the refrigerant is around it on the outside. So this is where the heat exchange happens. I think this is probably the most confusing part of geothermal is how do you get 70-degree air out of 50-degree ground? Like, what does the heat exchanger look like? It's a metal. We use copper or cupronickel. And water flows through it. It's a rifled, so you get turbulent flow, and refrigerant flows around it so we can extract the heat. Examples of heat pumps, we have different examples here, but there's what's called a self-contained package unit. So that's where your compressor and your evaporator are connected. So it looks like a refrigerator. You can go into the manufacturer's lounge. You can see examples of heat pumps in there. I'd invite you to do so if you'd like to learn more. The heat pumps come in different configurations. You can get a horizontal unit, or you could get a split system. So you can have a separate compressor where you would run a refrigerant line and place an air handler in an attic or closet or something like that. It doesn't have to be a self-contained unit. And then also we show here a water-to-water machine. This is just a compressor. There is no blower. There is no air coil because we're just making hot and cold water. So these systems get piped to a storage tank to store that hot or cold water. So here's a little graphic that kind of shows what a unit looks like in heating mode. So we can see coming off the loop field, the red lines are relatively warm loop fluid being circulated by a pump. It goes through the heat pump heat exchanger. The refrigerant goes through a refrigeration cycle. We're sending hot refrigerant we use an aluminum air coil. And then as the return air flows over that hot coil, the blower blows the warm air into the house. So I hope that makes sense. And then at the same time, we can look at the cooling mode. So in cooling, we're basically pumping the hot air. You're taking heat out of the air and moving it into the ground. So we've got relatively cold ground coming to the pump. We have a colder air coil. We have hotter air flowing over that relatively cool coil. When that happens, air conditioning mode, you get condensate. Water drips off that coil into a little pan. We have a little condensate pump. It pumps out. And then you blow cold air into the space. This graphic, I should also note, because it's our next section, talks about another part of the system, which is domestic hot water. This is an added feature that geothermal systems have, where you can reject heat to a storage tank and offset your hot water consumption without, you would still need a primary system with a desuperheater, but it's a way to offset your total usage of whatever your primary system is. So here's an example. We call that kit, it's an option when you buy a heat pump, an optional desuperheater kit. The way we like to see it installed is you have a two-tank setup. So you have a buffer tank that is filled with cold water, and then the cold water gets pumped through this hot wasted heat from your desuperheater, and that acts as the cold water in to your primary system. So you're sending hot water into your final domestic hot water system. Or you can get a 100% dedicated domestic hot water machine. The company I work for and other manufacturers will make a small water-to-water unit that'll have a special heat exchanger. It'll look a little different than this. There'll be an air gap between where the refrigerant and the water touch. In case there's a breach, you're not gonna get refrigerant in your potable water. And then you can pipe that direct to a storage tank without needing a buffer tank. We'll move on to the earth loop circuit. So this is probably, in a way, one of the most interesting parts of GEO because there's many options. And there's no best option. It's really whatever works best for that site. So we have examples here. We have a horizontal loop, a vertical loop, a pond loop, and then the bottom right picture shows an open loop, and you can see it's tying into an aquifer. So we'll talk a little bit more about these. But in a closed loop system, we use a pipe called HDPE, a polyethylene high density pipe, PE 3408. It's got SDR11 that is relative to the wall thickness and pipe size. And typically geothermal systems use 3/4 inch diameter pipe up to 2 inch or beyond. Residential systems are typically in that 3/4 to 2 inch diameter pipe. All pipe connections are made with 500-degree heat fusion, so it's very, very resilient. This is the same piping they use for natural gas. So they use a blue pipe, we use a black pipe, but that's, I think, in a way, one of the reasons gas utilities are exploring geothermal. You know, they're a distribution company. They use high-density polyethylene pipe. They're just moving gas, and we're just moving antifreeze and water. So they're very similar in the way that they operate. Here's an example of a horizontal system. So here's a house. You would dig typically below the frost line. So New York State, we're looking at 4 foot is average frost line. Systems will have an average depth of 6, 7, or 8 feet. You lay your circuit piping. You have a header pit where you connect all your different circuits together, and then you typically penetrate a supply and return line, so 2 pipes coming in through your foundation, and that gets piped over to your equipment and your flow center pump, which circulates the fluid through the ground loop. So this is just one example of a horizontal system. Here's another example. This is a horizontal slinky loop. So instead of running straight pipe, you can coil the pipe together, you can roll it out in a ball, but similarly, you're gonna go down at least 4 feet, you're gonna be below the frost line. An advantage to this system is because you can roll it in a ball, you might not have to get into the trench. So people can stand on the side. It's a little bit safer at times. Another system which should be more utilized in New York State, honestly, is the horizontal bore. So this is how they get gas lines into a house. They have a boring machine where they put the pipe on the end and it'll go under the surface and it'll loop it back. And you don't have to disrupt the surface of the ground. In a horizontal system, you have to bring in a backhoe, excavator. You're disrupting the grass. It's gonna be, you're moving earth in a big way. This system, you don't have to do that. You're sliding right under the surface. This is the most common system, I would say, both residentially and commercially. This is a vertical closed loop. This is the pipe. This is what it looks like. Supply and return right down a hole. You drop that in a 6-inch borehole, and there's only one fusion at the bottom. These come pressure tested. After you sink the loop, you cut the tops off, and then you fuse horizontally under the surface. So these systems, there's nothing exposed. You would never know there's a system there because it's completely buried at least 4 feet down. Another system is pond loops. If you have a pond on your property or you have access to a place you can put a loop, this is one of the most cost-effective loops because you don't really have to dig, you just have to sink coils of pipe. So great option if you have that available to you. Last one would be open loop. So this is where you're directly taking water out of the ground and then pumping it through your heat pump and putting it back into the ground. So this was very popular originally when heat pump technology started. A lot of big commercial buildings have utilized this technology. And just due to aquifer changes, water quality changes, the maintenance associated with it, I've seen this technology, though very efficient, become less used. It requires more maintenance because you are running groundwater right through a heat exchanger. You're gonna get, a reaction of the minerals and things in the water with your metal heat exchanger. So here's an example of a typical closed loop system. You have in this picture, a self-contained package unit. So coming in from your loop starting on the right, our units have external flow centers. Some heat pump manufacturers put their flow centers internal. So it would be within the cabinet and you wouldn't see that there. But it's a required part of a closed loop system. You need a way to circulate that earth loop fluid. It goes through the heat pump, you've got your unit with your ductwork connected, and here it shows your domestic hot water connection to a storage tank. In closed loop systems, you need to put antifreeze in it. These systems, typically you want to run a 15-degree freeze protection, so you can pull enough heat out that the equipment will shut off when it senses a 15-degree temperature. So types of antifreezes that are used are Environol, that's an ethanol-based antifreeze, methanol, and propylene glycol. Here's an example of an open loop system. You can see in this picture there is no flow center. That is because in open loop systems, you're utilizing the pump that's in the well. So open loop systems, you have a wellhead sticking out of the ground. There's a submersible pump in there. You're using that to pipe to a pressure tank, and from there, you're piping that over to your heat pump. So it's a little bit different of an installation. Still operates the same with, in this case, ductwork, but your loop side has a little bit different piping. Some other applications of geothermal, obviously commercial applications, those can be much more complicated. Trying to keep it very basic here today. So you've got hotels, retail, apartments, condos, resorts. We brought a unit in our WaterFurnace booth that's been used in apartments and condos. It's a console unit, so I'd encourage you to come check that out, just as a different type of heat pump. It's not the box type looking. It's more of a sleek wall-mounted unit. Hospitals, nursing homes, you can use for snow melt and pools and spas. The industry itself, who's involved in geothermal? We've got contractors, architects, manufacturers of different types. We've got our GEO Consortium. That's our group that advocates for tax credit policies in Washington, D.C. for us. IGSHPA, the training hub that trains people on how to properly install the systems, as well as electric utilities. So I'm just going to wrap up here. The key benefits, the key takeaways of geothermal, it is the most efficient heating, cooling, hot water system you can purchase on the market. It's quiet. All of the equipment sits inside. There's no outdoor equipment. And because of that, there's less maintenance, and the equipment lasts longer. So the average life of a water source heat pump through ASHRAE is 24 and a half years. Manufacturers like I work for, we warranty the heat pumps for 10 years. So the products come with a very long warranty due to the long expected life. They're safe and clean. There's no combustion, no fumes, very clean indoor air due to that. And a side benefit is all the products are made within the U.S. So the contractors, the engineers, everybody we looked at on the last slide are U.S.-based companies, which I just think is a really cool thing. So that's it for me, and I'll take some questions.
Amanda, do you want to proctor us? Point us to any?
I don't see any hands.
Oh, no.
There we go.
All right. You're going to state your name and your question, and you're going to speak into the mic.
Mike Bayless, EnergyWise, Heating and Air Conditioning. You had showed us on a slide with low temperature radiation for a water-to-water system. What is the normal design condition for something like that? What is the performance on a water-to-water system? Because it's obviously not going to work with traditional baseboard radiation.
So low temperature systems are typically operating between 120 and 140 degrees. With the refrigerants that we use and the way our heat pumps are built, we can't really get beyond that 140 degree temperature. So that's why you need a special built radiator or baseboards. Traditional baseboards are typically specified for 160 to 180 degrees. They sell a product that basically just doubles the baseboard. So you're running a little bit colder water through double the distribution system. So you would end up replacing all of the baseboard.
Yeah, you would basically be replacing all the baseboard in the house to this low temperature baseboard. And then the cooling system, of course, would be just a water-based coil.
Yeah, typically, if you're going to keep your baseboards and stick with a hydronic system, the only way to get air conditioning is by adding a fan coil or like a wall-mounted unit, kind of like a mini split that runs off of water and would blow cold air on you.
Well, in most retrofit applications, you might have a traditional air conditioning system and traditional oil-fired boiler with baseboard, right? And then retrofitting that, okay, you put in a split system, but obviously there's zoning issues, there's other issues with an air conditioning design system for heating, whereas obviously a house has baseboard heat, might have multiple zones. It might be a more simpler, better application is what I'm driving at, to produce the hydronic heat through the water-to-water system and replace all of the baseboard in the house with this low-temperature radiation, and then just change your air handler into a chilled water coil system. Does that
yeah.
make reasonable sense?
That, people do systems like that all the time. That makes sense.
Thank you.
We got 30 minutes left of questions.
That's a lot of questions.
I'm just joking.
You'll be early for lunch. First in line.
Lunch starts at 12:30, so you might as well ask more questions.
I'm Donna with New York Geothermal Supply. Can you tell them the difference between an SEER and an EER? Because I know that's so confusing.
I don't have anything here on the seasonal energy efficiency ratio. That is used for air source heat pumps, where I believe they're basically looking at an average of heating and cooling performance. Not fully sure. I only sell geothermal heat pumps, so I'm not an air source expert.
So that would be a seasonal energy efficiency ratio?
Yeah, she wanted to
so
know
about
the
the
difference.
average of the season for that rating on the HRI. So it would be a little bit higher than the regular EAR, which would be that peak condition.
Thank you.
Behind you.
Hi. Andrew Kreshik, City of Troy. Just curious, when you're using an application of a geothermal loop system in a heat island area, how does that affect the efficiencies of the system?
So you're talking about a heat island where the air is very hot?
No, where the ground is higher, so your annual average would be higher than what
so
the
you'd be
general
looking-
area is.
You'd be looking here where your deeper earth temperature, you're not 50 degrees, you're more 60 or 70 degrees. So your ground temperature will affect your performance or your ground loop design. So depending on which your dominant load is, whether it's heating, which is typically residential systems are almost always heating dominated, and you're sizing your heat pump for heating. If you're cooling dominated, you would thus size your ground loop for cooling. So if you have a hotter ground temperature, that may benefit you for heating, but if you're sizing for cooling, that may hurt you, because it will be harder to reject heat to a hot ground.
Maybe you can explain the highest levels of temperature return and the lowest in the winter to the bore, which
Sure.
would help. That's kind of why these are really great.
So typically, like we showed before, the Energy Star, we're looking at, in a closed loop system, worst case, 32-degree entering water coming to your equipment. So typically, we're taking 6 to 8 degrees out of that loop. And then we're sending it back through the ground to recollect that energy, bring it back to your heat pump. So, worst case conditions in the winter depends on what you design for. Some people design for 32. I believe the IGSHPA standard is now 25 degrees. You can have a worst case condition of 25. And then the heating system, residential systems, you could be as high as 80 degrees in this area. For your cooling season, your ground loop coming in could be 80 degrees.
Right, so your lift would be better than an air source, and that's why these are more efficient.
Exactly.
Any other questions? Okay. Well, if you don't want to ask a question, we have 30 more minutes you can just talk to Amanda directly.
Yeah,
So-
I'll be hanging up here if you want to talk. If I have some examples of heat exchangers, if you're interested in what's in the equipment, you're welcome to stop by our booth in the manufacturer's lounge. So I appreciate you coming to my session.